Hello everyone! This time we are working on cosine, graphing the function cosine. So we're going to start with the parent function, which, similar to sine, looks like y equals cosine of x, or again, y equals cosine of theta. So similar to sine, and we'll see it's similar to tangent as well, our input is still going to be some angle in either radians or degrees, and our output is some fraction. So we're going to fill out a table and plot our points again. My recommendation for you is to actually pause the video here and copy down the table and plot your points. Again, I am going in increments of pi over 4 or 45 degrees. So I will be using the same scale as we did with sine. So on my x or theta axis, I'll be going 1, 2, 3, 4 for pi, and then 4 more for 2 pi. And then I'll count up 4 for positive 1 and down 4 for negative 1. So I'll give you a moment there to fill out your tables. Okay, so let's check our work. First of all, our tables, we'll see again some of those repeating values, some of the exact same ones that we saw for sine. 1, root 2 over 2, 0, negative root 2 over 2, and negative 1. The only difference is the order of those values. Now we'll see when we look at the plotted points, we end up seeing a very similar shape. But the difference is kind of where that shape starts. So as just a little reminder, I'm going to roughly sketch what sine is over top of this graph. So we kind of had, let's see, I'm going to plot myself some points here. We had this for our sine curve, and our cosine curve is there in blue. So it's offset just a little bit. Whereas the sine curve starts by going up, it starts at 0 and goes upwards, our cosine curve actually starts at this max point for our parent function, that's 1, and it heads downward. So our cycle is actually going to be defined a little bit different. Remember that just like sine, our cosine is a periodic function, so we can define the cycle and the period. Okay, let's look at what those are. Just like for sine, our period is going to be 2 pi radians, or 360 degrees, and that's again just the length, the horizontal length of one cycle. Like I was mentioning, for cosine, our cycle looks like this, where we start at our peak point, our max, we kind of head down, we loop around, and then end up back at our maximum point again. Okay, so let's talk about some of our key features that when we transform this graph we'll be looking at. So these kind of max points, those are two important points that we'll always be looking for our cosine graphs. We'll also be looking for this minimum point as well as the x-intercepts. So when we talked about the important points for sine, it's really the same things. We have our x-intercepts, our max points, and our min points. Those just occur at different spots when we're looking at cosine. So let's think about the transformation that we can do to our cosine function. Just as before, we're going to be reusing these a and b values when we transform cosine, when we make it slightly different, where a represents the amplitude, which again is kind of the height of that curve, or half the difference between our max and min. So if this is my cosine, let's see, I guess I graphed that kind of upside down. That's my cosine plot. Our amplitude is going to be this height. Okay. B also still represents how many cycles are occurring in 2 pi or in 360 degrees. And we can also determine the period using B by dividing 2 pi by B. So we'll look at an example. Here we are asked to graph y equals 4 times cosine of 1/2 theta. So first of all, we have a different amplitude. Our amplitude is going to be 4. Now that also tells me that my max value is 4 and my min value is going to be -4. Notice that when my parent function is used, y just equals 1 times cosine of 1 times theta, my graph just starts at 1, goes down to -1, and ends up back at +1. So my amplitude, A, is equal, or my A is equal to my amplitude. So here, our amplitude is 4. Okay, what about our period? Let's think there. Well, let's use that formula, 2 pi divided by B. B here is actually 1/2, so 2 pi divided by 1/2. Ooh, a complex fraction. Let's see if we can simplify that. Complex fraction, well, we're dividing by this fraction 1/2, so we could also just multiply then by the reciprocal, 2 pi times 2 over 1. So that will simplify to 4 pi. This tells me, and I'll write that that's equal to P, or period. This tells me that one cycle is going to be completed in 4 pi. So it's actually going to be kind of stretched out compared to our parent function. So let's think about how we might go about graphing that. I have a set of axes on graph paper over here on my page. And I've kind of extended it because I know that my period is longer now. It's 4 pi. So I will go ahead and actually just count, make my y-axis scale just by 1. So 1, 2, 3, 4 will literally be 4 units up, and then -4 will be 4 units down. So I might, though, spread out my, my whole cycle a little bit. So maybe I'll still count by 4 for every pi. So 1, 2, 3, 4. Here's pi. 1, 2, 3, 4. Here's 2 pi. So that's only half of my cycle now. Here's 3 pi. And here will be the marking for my full cycle. So let's think about those important points. Our x-intercepts, our max, and our min values. So for cosine, remember we're always starting at that max. So we'll start at our max point, the top of our amplitude, 4. Okay, next up we'll think about our x-intercept. The x-intercept will occur right at pi. All right, then our minimum value, that's kind of the halfway point for us, that will be at 2 pi. Then we're going to have another x-intercept as we turn back around right at 3 pi. This is 3/4 of the way through our cycle. And then to complete the cycle, we'll be back at 4 pi, back up at our maximum point. So now the challenge of filling in this curve as nicely as we can. Let's see what I can do here. Okay. Yeah, you know it's not perfect, but I'm not asking you to be either. So that is roughly what we would be looking for the graph of 4 times cosine of 1/2 of theta. Okay, this is part 2, so we'll see you later with tangent. Thank you.